Hi, we've got another crowdfunding campaign for you. Yes, on the Choice of Champions Indiegogo flexible funding. Quite a few people asked me to have a look at this one and see if it all adds up. Let's take a look at it. It is the Matrix Powerwatch, the smartwatch powered by you. And look at this, looks fantastic. I want one, pretty jazzy. And look at this, a smartwatch that could be the harbinger of the future. Matrix Industries wants to free us from battery woes. Wearables can and should power themselves. Good on your IEEE Spectrum Gizmodo. Powerwatch's unique thermoelectric technology gives it a big advantage when it comes to accuracy. There's a new smartwatch in town and it's ready to make charging complete non-concern. Is eternal battery life long enough for you? The dream of the no-charge watch, and on and on and on it goes. Yes, it's a watch powered by a thermoelectric generator, and it can also measure calories via the thermoelectric generator as well by measuring your body heat output. So yep, it's a smartwatch with a thermoelectric generator, a TEG in there, and we've seen TEGs on the EEVblog before. Nothing special, and there's nothing new here at all. Several companies have actually produced thermoelectric generator watches a long time ago, but I think there's a reason why they don't make them anymore, as we'll see. Now, this is actually done by an impressive team, and you can go in and see their bios and everything else. These are all university professors, PhD researchers in thermoelectronic technology. So these guys know what they're doing, right? So I have no problems with the team whatsoever. And, this is not a scam, right? This, of course, you can power a watch from a thermoelectric generator, but this is the first smartwatch on the market, albeit a relatively simple smartwatch. It doesn't have a heart rate monitor or anything like that. It's got none of the fancy stuff. It's got no auto notification from your smartphone and things like that. But yes, it does have Bluetooth and an app, and you can actually sync it up, but it doesn't do most of your traditional smartwatch functions and things like that, unfortunately. So yeah, it's basically a watch with a stopwatch, and the whole key to it is that it can measure your calories because it's using the heat output from the thermoelectric generator. And hang on, what's this? Certified by Arrow Electronics. This entrepreneur received a design review with Arrow to ensure the campaign is ready for production. Indiegogo and Arrow Electronics are proud to offer this resource to help entrepreneurs bring products to life. Well, that ticks all the boxes, doesn't it? I mean, Arrow, huge company, they have obviously vetted this thing and it's fine. Or have they? No, if you actually go into Arrow, what is Arrow certification? They do a design for manufacturer analysis, i.e. the BOM, and stuff like that. And they're actually boasting, Matrix have actually appeared on the EEVblog forum to try and explain themselves, but they're not answering questions. And they've said they seem proud that Arrow has certified this thing because they reviewed the schematic. Well, sorry, no, it doesn't work like that. Of course, you can make a watch powered from a thermoelectric generator and get it made. It's no big deal. The whole point of this thing is, does it have a point? Actually, is there an advantage to powering a watch from a thermoelectric generator, or is it just a gimmick? And Arrow have not... That's not their job to actually verify that thing at all, whether or not it's worthwhile powering it from a TEG like this. So, yeah, they're just trying to, make it look fancy-pantsy that they're certified by Arrow. Doesn't really mean much.
Our world has an ever-increasing thirst for energy. Our machines,
and here we go, it's feel-good video time.
Yet most of the energy we use is wasted.
Oh, it's wasted.
Over 30 trillion watt-hours of heat per year are wasted by power plants alone, enough to power the entire world.
Wow.
And our environment is part of the collateral damage.
Save the environment!
Over 15 billion batteries are thrown away in landfills every year.
15 billion!
At Matrix, we wanted to create technology that makes the way we use energy more efficient and more intimate.
Awesome.
We wanted to start with a problem everyone has experienced firsthand. Feeling frustrated when your electronic device runs out of power when you need it the most.
There hasn't been
any innovation to solve this problem, and that got us excited to solve it using our thermoelectric technology.
Woo!
After 5 years and several prototypes, we're introducing
our
first product.
Fantastic.
The Matrix Powerwatch. It's It's a smartwatch that's powered by you.
Wow, it's powered by
It
me.
works by converting your own body heat to electric power. And the best
Save all
part
these
is
batteries.
you never have to charge it.
Never have to
The
charge it.
watch comes alive because it's powered by you.
Whoa.
We've done most of the hard work. We have a few dozen prototypes and a ton of data, so we know it works. The Powerwatch has been vetted and certified by Aero Electronics.
So as I mentioned, they actually joined the EEVblog forum, I guess, to try and defend themselves, and that's great. We love it when companies join the forum and share data, because as you saw in the video, they have tons of data that proves it works. Well, yeah, we know it works. It's a thermoelectric generator and a watch, you know, it's definitely going to work, but is it practical? And they actually seemed quite offended that anyone would dare question the practicality of the product and whether or not it's the thermoelectric generator is simply a gimmick. And we asked them, several people on the forum, including myself, asked time and time again, just provide the data. We'll change our minds. Just give us the data. And nope, they simply refuse to give it. So yeah, you can see what's coming. But hey, all we need is a couple of bits of data on this thing to allow us to do some quantitative analysis on to see if it's a viable and practical product and whether or not it's just a gimmick or not. So we have that data. They've actually provided that in various news stories and other things like that and their Indiegogo comments. So let's go. So let's run the numbers, shall we? Back of the envelope, ballpark stuff. Actually, we're better than ballpark because we've got some really good known numbers here. So let's go through it. It won't take me very long at all to show what a gimmick thermoelectric generation for watch actually is. So the known numbers that we've got. The operation takes about 20 microwatts or so. I got this, I speculated this on the forum, EEVblog forum, and they said, yeah, my numbers were fine. They didn't dispute that. So let's go with 20 microwatts operation. The sharp memory LCD, they're really low power. It's about 4 microwatts plus the Apollo Ambic processor that they're using. It's an ARM Cortex, whatever, something or other. So let's take 20 microwatts. They've said that is basically fine. Now, they've released a figure for the battery inside, the capacity of the battery, 200 milliamp hours. That's going to be a lithium ion jobby at 3.7 volts. That's 740 milliwatt hours capacity in the internal battery. Now, they've also said in the comments on the Indiegogo campaign, somebody asked, hey, what's the power output you get from the thermoelectric generator? And they said under basically best case conditions, a cold, windy day during exercise, they got 500 microwatts. So that is presumably the generation figure. That's not how much that after the losses in the DC to DC converter, everything else, that's generation. And that's their best figure. That's the best pie in the sky, best case figure that they can get. But we'll run with that. We'll be generous. We'll run with that. So we've got 3 good known figures here. Now we're going to assume that it generates 50 microwatts at rest. So I'll give them 50 microwatts. They're experts in these thermoelectric generators. They're researching them, manufacturing them, so they know what they're doing there. And you're going to be resting for about 15 hours a day because you're not going to wear it when you're sleeping. You're sleeping, it's going to reach thermal equilibrium, so it's not going to generate any charge, and nobody wears a damn watch to bed, and you're lying on it, stuck under the pillow, it's whatever. It basically, even if you wore it to bed, it's not going to generate anything. So let's say 15 hours a day, 750 microwatt hours per day generation at rest. And I think that's pretty generous. So now we can do the calculations here. Let's assume that you're really active and you do 1 hour solid hardcore exercise a day at their best case figure of 500 microwatts. Okay, that's 500 microwatt hours per day. That equals 1.25 milliwatt hours per day total if you add the rest plus the 1 hour of exercise a day. That's being generous. Wow. But you don't get a free lunch, of course. It has to run 24/7. Let's assume it doesn't go into its deep sleep mode. I want my watch to be always on. When I look at the damn thing, I want there to be time there. So that's the 20 microwatts operation times 24 hours a day. That's going to use 480 microwatt hours. So you've got to subtract that from your 1.25 milliwatt hours here, or 1250 microwatt hours per day. So 0.77 milliwatt hours per day that you have available to store in your battery. And once again, I'm not including any losses in the DC to DC converter or charging process or anything like that. So I'm being very generous. So even if you're flogging your guts for an hour solid exercising every day and you wear it all day, basically, except when even if you were sleeping, then you're only going to get like less than 1 milliwatt hour per day available to store the battery. Now I know this thing actually goes to deep sleep when you take it off, so presumably it doesn't update the time or anything like that. It saves all your stuff and things like that, but when I take a watch off, I don't want the time to vanish. I want it to be there. But anyway, let's assume that you're sleeping 8 hours a day, you take it off and it's going into low power mode where you haven't got the 20 microwatts for the 24 hours. You've got to subtract 8 hours of sleep time. But even then, assuming it drops down to basically zero, bugger all, it still doesn't change the overall calculation much. So let's assume that the battery went flat in this thing, but it's not supposed to, because just the low power operation plus Bluetooth doesn't take a huge amount either. It should never get flat, but let's just assume it did. For kicks, how long would it take to charge the internal 200 milliamp hour 740 milliwatt hour capacity battery in this thing? Well, 740 milliwatt hours divided by 0.77 milliwatt hours per day, 961 days or 2.6 years to charge this thing from flat. But that's not the intention, just did that for kicks. The whole idea of this watch is that it's supposed to generate more power by wearing it than it actually consumes, and therefore you never have to change the battery. But hey, let's just assume that you used it as a normal watch with no Bluetooth functionality, just a normal smartwatch. Maybe it's running a little app or doing something like that. At the 20 milliwatt operation, let's assume that it operates all day. Even a CR2032 single coin cell battery has got a capacity of 600 milliwatt hours. At 20 microwatts consumption, that's 30,000 hours operation. 1250 days, 3.5 years they could have powered this watch from anyway without the thermoelectric generator gimmick in it, and they get 3.5 years operation. Just like you can buy Casio watches, they get 10 years operation shelf life of the battery. And for all the physical space they've taken inside this thing for the thermoelectric generator, they could whack in a much bigger battery than a CR2032, or just made it thinner. But then, hey, they don't have a gimmick to sell it. And I think a lot of people are just going to be using it as a regular watch, because it's not like it has, heart rate tracking and stuff like that, or it's like a real smartwatch and that people use it for to get, email alerts and call notifications and stuff like that on your watch. It's got none of that, because it doesn't have much in the way of smartwatch functionality. So right there, as a watch that never runs out of battery, it is pointless. It is a gimmick. But hey, if you want a thermoelectric charging watch just because, it's cool or whatever, okay, that's fine. Knock yourself out, but don't pretend that it's, something special in terms of never running out of battery. This watch, sticking a regular coin cell in it, would never run out of battery anyway. So let's look what happens when we add Bluetooth, shall we? Bluetooth LE is pretty low power. There's a TI application note, which I'll link in down below, where they actually do measurements on one of their Bluetooth LE modules. Let's assume that, that's basically as good as you can get. They came out with an average figure of about 80 microwatts consumption or thereabouts, with a once per second continuous connection. So that's, reasonably good, but that's 4 times the operating current, roughly, of the actual watch. So, you wouldn't want to leave that on all day, every day. So let's assume that you actually had it on and continuously connecting like a regular smartwatch would, connect into your phone. Let's say they added these things, which I think they're talking about adding, more smartwatch capability in terms of, updating your from your phone and all that sort of stuff. Well, at 15 hours operation, then that's 1.2 milliwatt hours per day. That's like, getting towards double-ish of the energy that we're actually going to get out of this thing and store. And remember, I was being generous with no losses. So now you can probably understand why they haven't built this functionality in, like continuous smartwatch Bluetooth polling, because I don't think they're going to generate nearly enough power in the thermoelectric generator to keep this thing charged and to get their infinite battery life. But even if you use Bluetooth continuously 24 hours a day, let's have a look at what just a regular primary coin cell will get you. Let's say you used a bigger coin cell rather than a little wimpy 2032. Let's say you used a CR2450 here in blue. I've got the figures now. That's around about 2,000 milliwatt hours capacity. Let's assume that you had Bluetooth all the time, 80 milliwatts, 24 hours a day, 7 days a week, 365, plus the 20 milliwatts operation for the thing continuous, none of this deep sleep rubbish. You've got 100 microwatts consumption. That will still give you, that battery will give you 20,000 hours of operation, or about 2.3 years. Why on earth would you need a thermoelectric generator to charge an internal battery? It's not environmentally friendly. You've still got the lithium-ion battery in there. It just doesn't make sense. No matter how you look at this thing, it is nothing more than a gimmick designed by, of course, professors were at the university working on thermoelectric generators. They've been working on for so long. It's their life, it's their passion. Hey, and that's great. But now they've tried to just shoehorn that technology into a watch, making it out like it's the greatest thing since sliced bread. You never have to change the batteries. Whoop-de-freaking do. Just put a regular coin cell battery in there and you'll get many years of battery life. Watch is probably going to break before then, especially it's designed to be like an exercise watch. It's like, give me a break. And they also claim that the watch is going to be one of the most accurate calorie counters out there because it's measuring the heat output from your wrist. Well, I want to know exactly the data behind this and how they can prove that, because I'm skeptical of that one, because the autonomic nervous system, as Thunderfoot is shown in his video, during exercise, the energy will drain out, the heat will drain out of your arms and then for a while and then go back in. How is this accurate? How does their algorithm account for your body doing this based on what particular exercise you're doing? I don't think it's going to be accurate at all. I'd love to hear their feedback on that one. I asked them on the forum, no response. And before you go and say, oh, I've got some sort of calculation wrong, they have basically admitted that there's nothing wrong with my calculations. I did these on the forum previously. They were involved in discussions. I asked them to provide their data. They wouldn't do it. They said they'd provide it to me privately. Come on, give me a break, right? The numbers add up. They have confirmed them, and well, you might as well just stick a bloody battery in the thing, because the thermoelectric generator, gimmick. I mean, this is pretty basic stuff that anyone can do, and these guys know it. They know that it's a gimmick, and they want to get, funding for researching further products that they want to do. But hey, they're taking people's money for this smartwatch. People are going, wow, it never needs to change a battery, when they don't realize you could have just done that anyway with a primary cell. So yeah, but they won't tell you that, because then it wouldn't sell. So can a thermoelectric generator like this actually power a modern digital watch just driving a smart memory LCD? Well, of course it can. Spoiler alert, anyone who knows anything about thermoelectric generators, modern low power processors, know this is easily possible, and I'm going to demonstrate it here and we can get a few numbers. Now what I've got here is the, you've seen this before on the blog, the Wurth electronic design kit. Board I've got here is actually a linear technology board. I'll link it in down below if you want to have a play around yourself. This has got different energy sources. A thermoelectric generator here from CUI. It's just a jelly bean one. I'll link in the data sheet. It's got solar cells as well and piezoelectric generator inputs, but we've only got the thermoelectric generator actually hooked up here, and here's the schematic for the circuit we're using. It uses a linear technology 3801 low startup voltage DC to DC converter, fairly typical in one of these thermoelectric generator applications. And over here we've got an EFM32 Giant Gecko processor. This is an ARM Cortex M3 processor driving an LCD here. Batteries are disconnected, of course. It's being powered from our thermoelectric generator, and this multimeter here is measuring the input voltage from the output voltage of the thermoelectric generator, and this one here is measuring the output of our DC to DC converter, which is normally 3.3 volt regulated. Now, of course, it's not generating anything. In fact, it's generating a negative voltage here because the heatsink is just heat up a little bit above the ambient, because I've actually been playing around with it, putting my hand on it, and the heat from my hand, the energy from my hand is transferred through to the heatsink, and as you see, that's slowly dropping back down now. So it's actually working in reverse and generating a negative voltage. But of course, if I put my hand on there, then this top plate, the positive plate, will be at a higher temperature than the heatsink, and it will start generating a voltage generating current. And as you'll see, it'll power to the circuit. So let's go. And boom, 30 millivolts, and it should get there, it should get there. Hold on to your hat. 3.3 volts, bingo. There you go. It's 19.7 degrees C here in the lab. By the way, if you just wanted to know what that's, 68 Fahrenheit for you Yanks. And of course, if I take that away, you'll see it start to drop, but I've got some output capacitance on here, small amount of output capacitance. And of course, this micro can work down to lower voltages, so you'll see it eventually fade away like that as the thermoelectric generator reaches thermal equilibrium again. It'll go back down to zero. So bingo, just using a jelly bean thermoelectric generator, we can easily power an ARM Cortex M3 processor, albeit a nice little EFM32 low power jobby here, and an LCD, no worries whatsoever. Hey, but they use an e-ink display. They're even lower power than these LCDs, kind of effectively. So let's try that. So what I've got here is an EFM8 Sleepy Bee, and it actually uses a, I'm not sure the resolution, I think it's 128 by 128 there, Matrix are using the 240 by 240 sharp memory LCD, but it's the same sharp memory LCD, and once again, I can put my hand on here like this. Yes, I haven't got it on my wrist, we'll do some measurements like that in a second, and it actually just goes into reset here. Oh, you kind of saw it flick on like that. It's because it's taking gulps of energy and there's not enough output storage cap. I need to put more capacitance on it. I've just built up the charge on the output capacitance. It's got a whole bunch of 100 mic ceramic surface mount caps on the bottom of there, and it'll briefly power this, but it won't last for very long, but you'll get the idea. There we go. Well, you saw it. We even displayed a clock. Beauty. So how much power can a TEG like this generate? Well, I've got measuring the output current here. I'm just shorting the output with my microamp range. This has got a 1.5 ohm output resistance on this particular one. And once again, we're measuring the TEG voltage like this. So I'm actually going to put my hand on there and going up. And turns out, what do we got? About 400 odd microamps, 40 millivolts, let's call it that. So you multiply those, and it's not terrific. It's only like, 15, 16 odd microwatts of that order, but that's what you'd expect, and it's enough to power, micro-powered, modern micro-power processors and stuff like that. It's basic energy harvesting 101. But of course, that power is just the output from the thermoelectric generator. That doesn't include any power losses in the DC to DC converter at all. And if we actually disconnect our TEG from the circuit, yeah, we're going to get more. We're going to get, 700 odd microamps, something like that. So we're talking about 50 odd microwatts. But I know what you're thinking, Dave, what does it produce on your wrist? Okay, I've got it on my wrist. I've had it there for a bit, and I've got it, not really tight down, because you don't wear your watch tight, and of course it's on the top. My arms aren't particularly hairy. They're a little bit hairy, but nothing out of the ordinary. And no, I'm not going to wear my watch on the bottom where it has no hair. That's ridiculous. People who wear that, silly anyway. And we're getting about 240. So, 240 microamps times 24 millivolts there. Well, we're only looking at, just over 5 microwatts. It's bugger all. But of course, they're going to have a better thermoelectric generator than these. These are, leading research group in thermoelectric generators. I'm sure they got a pretty decent one. Anyway, it's of that order. Alright, so let's see if we can get some data on this baby when I exercise. Now, I'd probably strap some multimeters in my backpack, data log, go for a bike ride, something like that, but unfortunately it's 36 degrees outside in Sydney today. That's Celsius, by the way. So yeah, it wouldn't generate any power at all. It'd just be at thermal equilibrium and it'd generate bugger all. So I'm in the lab here. It's relatively cool. I've got the aircon on, so there is some sort of airflow going around the room, so it's on full, and I'll just exercise in the lab here. I'm generating about 16 microwatts at the moment. Once again, it's not tightly coupled because I don't want the heatsink to touch my wrist and all that sort of stuff, so I'll see what I can do and see what I can generate. It's going to be fun. And I've actually got to be careful because I've just had a knee reconstruction, so I'll take it easy. But anyway, well, here we go. Standard lab jumps. And I'll just keep going. Still going, but you can actually see it starting to drop, which is not unexpected. I'm actually min-max recording here, so we'll be able to get the maximum value, but I'm not surprised it's dropping at all, and I'll explain that once I'm done. And if you're curious to see what's going on here with the flare, I'll see if I can get it. Sorry about any reflections. Okay. Heatsink, about 27 degrees, something like that. My hand, my arm, not a huge amount. As you can see, though my hand, there's a lot more blood flow in my hand. This is why, you rest your hand on it before. It's going to work fairly well. But in this case, so what starts happening as you exercise is the autonomic nervous system starts shunting blood around the body to various parts, and it'll actually suck the heat out of your extremities before it will actually pump it back in. So the longer you exercise, you've got to exercise for quite some time before it'll start actually shunting blood through to your arms and actually using the surface area of your arms to actually get rid of your body heat that you've built up during exercise. And I'll actually link in a video by fellow blogger Thunderfoot, and he's done an excellent video on this where he hops on an exercise bike and for like 20 minutes or something, and you can watch the blood actually drain out of his arms, and his arms actually get cold, and then as he exercises for longer, they'll actually start warming up again. It's really fascinating. If you do short, brief periods of like burst exercises, then you're probably actually going to drain more heat out of your arm than it's going to heat up. So that's going to cause a real problem. And let's have a look at the meters here. What have we got? Max, 38. Record, 38. That's like the best I could, 380 microamps, 38 millivolts. That's the best I could get to during that exercise. Granted, I wasn't exercising for half an hour, but a good 10 minutes, and that's the best I could do. So roughly, we'll call that 15 microwatts using my just off-the-shelf tag here with my heatsink just flapping in the breeze. But no, I've got, as I said, I've got some aircon, air circulation in here a little bit. I mean, maybe I could strap a fan on there and blow air across to simulate riding a bike or something like that, but yeah, it's not terrific. But granted, they're going to have a better teg and better thermal design than my little MacGyver solution here. So yes, the product is going to work, and yes, they have got the right people on the team. They're very likely to produce, the final product. I have, quite a lot of confidence that they'll come through and produce it, and it'll probably be a half reasonable product. It's just pointless, the thermoelectric generator. Meh. Anyway, if you want to discuss it, down below. Catch you next time.